point out one thing as to where you'll find some things. So, and I'll put a little link or something on here maybe to make it easier. Most days in class, what we're going to do is we sort of have a guided sheet that, in addition to all these warm-up videos and stuff that we, me and Dr. Insaldi and Dr. Gates, over the last couple of years have spent a lot of time writing and revamping and editing these things. In addition to the warm-up type things in class, what we're going to do is often sort of follow a what we call notes with holes. And so I printed these for the first day for you guys, and I'll hand them out obviously in a minute. But the PDFs of them, I'm just going to put up on Canvas. So here's where you get to them, and this will be relevant for those of you who are at home. Files. You go to the Files tab, and then you go to Class Worksheets, and right now there's only one of them, Calculus Preview, and that's today's, obviously. And then as we get into the chapters, I'll put some subfolders and kind of trying to organize it here. So this is particularly important if those of you who are at home and aren't physically here for me to hand you a copy of something, then that's where you get to them. And yeah, so what I would recommend that you guys get, if you don't already have one, is a 3-ring binder, because I've hole punched them, and that way you can kind of keep them organized. So, all right, so let me pass these things out. And I will refrain from doing the take them and pass them back just for quarantine purposes. Probably. Let me look. Not in my bag. I do have a pen. Yeah. All right, so yeah, that's what we're gonna do. So I'll put this up on the one screen, and then we'll write notes on the other. Okay, so first off, how'd the Edfinity demo and the first warm up go? Kind of make sense how this routine's gonna go. Not rocket science. And you guys hopefully also got started on the review exercises to get you guys ready for Friday. Because remember, next time we're doing our fun and exciting exam. Yeah, first day. Okay, but let's reiterate. What happens if you get a 0 on it? Which could very well happen. Yeah, you do them again, right? So this is the beauty of this sort of standards-based grading, is that we don't give zeros, we give not yets. Right? Now, because these are the prerequisite skills, right? This is pre-calc stuff that we'll be doing. The getting it should not take all semester, right? It should be pretty quick that we dust out the cobwebs from high school and get them back into your head. But the calculus stuff, right? You don't get it this time? It's okay. Try again next time. So anyway. All right, well, so let's talk about these things called bottle graphs. So let me go over to the iPad and switch the input on the OBS, Elgato, and double check that it is in fact switched over. Okay, looks good. And let me get the Twitch chat on. I really need a second computer for this, but it's okay. Okay. So looks like, do we have anybody online this morning? We should. Anyway, those of you who are at home, if you could just type in the stream chat, and that way we'll know who's here. Okay, great. So yeah, we're going to talk about these things called bottle graphs. So on the sheet there, you've got this flask-looking thing, which I'll just draw a um, crude imitation of, right? So imagine this is like one of those flasks in the lab. It's sort of got a sphere and then a cylinder on top of it, right? And so what we want to do is let's let this axis be the h-axis, okay? So if I were to fill water or some other liquid into the flask, right? Obviously, when the height is low, the volume is also pretty low because I haven't put much into it. And as the height increases to sort of its maximum value, then we end up with the full volume, okay? So what we want to do is we want to draw roughly the graph that relates the height of the liquid to the volume of the liquid, okay? Now, based on what we just said, where should the graph start and end? It should probably start here, right? Because if the height is 0, well, we haven't put anything in. And it should probably end, like, say, up there, whatever the actual maximum volume of the thing is. It's the stuff in between that's the fun part. Okay, so why don't you guys take a minute and sort of sketch, looking at that well, it kind of looks like a bong, but not that we would ever say such things. Um, yeah. What kind of graph do you think it'll look like? Okay, so take a minute and sort of sketch an idea, and let's sort of see what you guys get. You got anybody online with this? Oh, looks like just me. Huh? Well, okay. Can you be? What do you mean? Like, okay, so something like this. All right. Any other thoughts? I'll pick a different color and remind me your name. Alex, right? Okay, this is the Alex graph. Any other ideas? Yeah. Okay, so I think it's probably clear that when the height hits this number, from there on, what should we see? A straight line, right? Okay, and that makes sense because the top part of the bottle doesn't like expand or contract, right? So the rate at which it would fill would be sort of a constant. Okay, so that part I definitely buy. What about up until then? At the very beginning versus the middle of the thing, what kind of behavior should we see? Yeah. Does that make sense? Okay, and then, so it would go faster at the very bottom, then it would start to slow down and reach sort of a slowest rate of height increase um, as you get to this point. And then what should happen as we go up? It should speed up again until we hit the sort of constant amount. So it should look something sort of like maybe this, roughly. Okay, but does that kind of idea, that thought process make sense as to, um, or actually, you know what? I drew this backwards, guys. I drew the axes backwards. Uh, yeah, okay, this is what happens when you teach math without coffee. This should be the h-axis. Um, and so the reason for that is if I'm adding liquid to this, let's imagine that I'm adding the rate at which I'm adding liquid is constant, right? So like I've got like a hose from the tap or something. Um, and so the volume change is constant, but then the height change is either going to be the thing that speeds up or slows down. Okay, so yeah, that's what I meant. All right, does that kind of make sense though? What we're getting at? Okay, so that's sort of an idea of, we're actually sort of talking two pieces of calculus uh, in spirit here, right? We're talking about rates of things. Okay, there's half of calculus. And also we're talking about filling things up or adding things up. That's the other half of calculus. Okay, which is why this is sort of a perfect kind of preview activity to kind of get us going. Okay. All right. So does that make sense? That sort of process? That okay? Good. All right. So if we look down at the second thing on here, let me do this. Let me take that. Take Canvas, and let me pop open a new window. And that way we can have, oops, that way we can have both things on simultaneously. Wow, would you look at that, right? Yeah, I know, right? Um, yeah, I really need to either get a second iPad or a second computer so I can have Twitch on one thing and then everything else. But I think it would be kind of ridiculous if I have to start carrying around two laptops. Hmm? I did, but actually, what I need to get is one of the M1, like an M1 MacBook Air. Then I'll be in hog heaven. So, um, because the M1 is ARM architecture, which is what I teach in the architecture course. So, that'd be sweet. Okay, so let's kind of keep going down here to the bottom. So, let me kind of blow up this part of the figure, right? That what we've seen is that uh, the slope should be steeper. Back up. Right. So the narrower the vessel at sort of a horizontal like cross section of it, the steeper the graph should be, and conversely, the wider it is, the gentler the slope should be, and that's what we saw with sort of the spherical part, right? It was steeper at the beginning, and then it sort of leveled off, or slowed down until we hit the middle of that the sphere part, and then it sped back up until we got to the cylinder, and then the cylinder was sort of a constant cross section, and so we had a constant linear slope up until we hit the top of the bottle. Okay, so does that kind of make sense? Good. All right, so let's flip to the next page of it. Okay, so let's say that I have the following. Um, let's say that I have the following graph. Okay, just a perfectly straight line. So now I want you to do the backwards thing. I've given you the graph. I want you to draw the bottle. Okay, does that make sense? All right, now bonus points if you can be clever as to how you do this. So this is the curve we want. Okay, come up with the bottle. All right, so take a minute and kind of think about that. Is it too early for thought? Yeah, we'll get used to it. You guys aren't just going to sit on your butts the whole classes. Oh, whatever. Like a vessel to consume or to contain liquid. I mean, you can draw a oil canister for all I care, right? Or a shot glass. Huh? Yeah. Alcohol, what's that? Yeah, when I was in grad school, before class was talking with a bunch of students and about their weekend, and they're like, "Yeah, we had a great time." I'm like, "How can you guys have great times? None of you are 21." And somebody, I couldn't see who, quipped, "Our IDs say otherwise." This is like touche. And so then I drilled in on that and found out that it was actually, I was expecting their IDs to say that they were 21 or whatever. Now, they got fake IDs that would say that they were 19 because Iowa City had an ordinance that after 10 p.m. or whatever it was, to be present in an entertainment establishment, you had to be 19 or older. So they would get fakes to say that they were 19 but not 21, and then pregame before they went. And you got way less scrutiny from a guard or a cop if it said you were 19 than if it said you were 21. So it's kind of interesting. So, all right. So what kind of shapes did you guys come up with? Well, what would be the boring answer? Yeah, just the cylinder, right? That would work, but it would be boring. Okay, what else could work? Huh? All right. So if we did something like a cone up this way or that way. Okay. If we did a cone, all right, what's going to be the problem with the cone? Yeah. Yeah. So the only way that the whole thing is going to be linear is if every horizontal cross section has the same width. Now, a cylinder certainly does that, but what else could I do? Yeah, or I could do like a sideways cylinder, kind of like that, right? So, um, or my art skills aren't very good, but one could imagine that I could have like a bendy thing, like one of those bendy straws. Yeah, the width across each cross section would be the same, but it would be bendy in whatever direction. Okay, so yeah, so cone's not going to work. We've got to have the cross sections all the same. And so the only way that the cross section can look different is if the graph isn't a straight line. Okay, does that kind of make sense? Right, so here we're kind of thinking the backwards process from making the graph in the first place. And this sort of uh, going back and forth kind of approach is something that we'll do quite a bit uh, in the semester, right? So it's, given a thing, excuse me, how fast is something changing versus if you know how fast something is changing, what's a thing that might have given you that rate in the first place. Okay, so does that kind of make sense? Yeah. All right. Okay, so let's um, let's scroll down just a little bit, and what we see is we've got this um, the first shape, which is basically like a cone with the tip chopped off, right? Um, versus sort of a cylinder, and roughly speaking, does it look like the volume of the um, cylinder and the volume of that chopped off cone, do they look like they're going to be roughly the same? Like the total volume? Okay, I mean, maybe it's not perfect, but you'll humor me here, right? Okay, so what we've got there over on the left is sort of the dark line represents the bottle graph that would be associated with the chopped off cone. And then the straight line would be the bottle graph associated uh, with the just cylinder, right? Okay, so as we saw before, what happens if what does our graph look like if it's just a uh, constant horizontal cross sections, straight line, okay, of whatever slope. and that if the cross-sectional area changes, then is when we get curvy bottle graphs, excuse me. Okay, Gucci? Okay, so, right, even though the total volume of those things might be the same. Okay, so because what we're not necessarily concerned with the total volume, we're concerned with how quickly they fill up. Okay, so let's take for a minute that, well, a couple things. What is the slope of that straight line part? In the picture, what does it roughly look like? Yeah, 1, right? Is that, okay, whatever, right? But it's some slope. Is there a place along the curvy line where the slope is the same? Okay, so first off, what does it mean to talk about the slope of a curvy line? The curve part, right? What do I mean when I say that? Yeah, either take a segment of it, or can I draw a line that's tangent to it? Okay, so and the segment of it, like, which is what we actually have here. We have a really big, like, we got 2 points along our curve, and I could connect those with a straight line, right? And that straight line has some sort of slope, which we could calculate. Um, if I drew a tangent to it, so let me kind of sketch what I mean here. Um, and you guys remember what tangents are from, like, geometry in high school. So I don't mean the trig function tangent, but let's say that I had this and I have that, right? So this slope is whatever, 1, roughly in our picture. Is there a place where, barring my crappy art skills, the uh, the slopes are the same? Yeah? I mean, it's kind of roughly where I drew it, right? All right, where is it on the bottles? Like, what's the special point on the bottles where that's going to happen? Huh? Okay, the next, so elaborate. What do you mean specifically? Okay, keep going. Owen? Exactly. This intersection point right there. Huh, that's interesting. Okay, guess what you guys just discovered? Something called the mean value theorem, which we'll talk about later in glorious detail. Okay, now let's say for a minute that we've got this chopped off cone looking bottle. Okay, so could I think of that chopped off bottle as being like the following? Okay, so imagine, have you guys ever seen, like, pictures of, like, real early pyramids in Egypt? Right, so what do they look like? They're stepped, right? They're not perfectly sloped the whole way. So let me actually just draw a pyramid, right? So let's say this is an Egyptian pyramid versus sort of an early step pyramid. Okay, could I sort of think of this pyramid as being a step pyramid just where the step size is really, really, really small? Okay, and so the idea would be, if I sort of zoom in on a shape, like, let's say that I zoom in on let me draw something curvy. So let's take the bong that we were doing earlier, right? If I zoom in on, say, okay, there's my crappy magnifying glass, right? I expect at the end you guys are going to be like, in the evaluations, Dr. McKinney's art is so fantastic. He should be in like the Louvre and the Centre Pompidou, even though it's closing for a while. No, yeah, they're going to do some renovations and stuff. And honestly, this is just as good a time as any because it's not like anybody's going to it right now anyway. Huh? Oh. I haven't been to the Centre Pompidou. I've been outside it, but I didn't. I never went in either. I went into the Louvre and uh, actually went to a bunch of science museums when I was in Paris. That was really cool. Um, yeah. Okay. So that's my cheesy little magnifying glass. But if I were to zoom in really, really tiny on that, what would I actually see? It's not straight, but if I keep zooming in, it's actually going to look straight, right? Now, it's not what I'm not saying is that this entire segment is straight. I'm saying that when you zoom in on it, really, really detail, the difference between a curve and a straight line is going to be so negligibly small that you wouldn't be able to tell the difference. Okay. So, in a sense, we can almost think of this thing as being like a step pyramid, right? Just where the step width is really, really tiny. Okay. And that's going to be exactly how we think about this idea of slopes to lines, right? So, let me go back up to here where we drew our tangent line at this point. Okay. So, what I mean there, or one way we could think about it, is if I were to, so let me just draw this nice and big, right? If I were to zoom in on this little part, what would I see? Yeah, it would look really close to a straight line. And if I zoomed in further, it would look more and more and more straight. Okay. Okay. Well, that's good because how do you compute the slope of a straight line? X2 minus x1, right? The rise over run. Okay. You got 2 points, you know their coordinates, and then you just do the formula that he just said, right? Rise over run. Okay. But we need 2 points to do that. So let's take, for example, here. So the formula that Don said was something like, well, if those are the two coordinates, then what's the slope of that line? It's that fraction, right? Okay, so that's our rise over run. All right, and so we remember that from high school, right? Yeah. Okay. Well, what calculus is in the business of doing is say, okay, we're going to do that thing, but we're going to do it when x1 and x2 are closer and closer and closer together. Because the closer they are, the closer that straight line that I've labeled M here would be to the curve. Like right now, they're really far off. But what about if x1 is here and y, like the 2 points are where my two fingers are, right? What's the slope going to be in comparison to the slope along that curve? Really dang close, right? And then the closer we make it, the better it gets. So there's the third big idea of calculus, the idea of a limit. Okay, so that's where this is all going. Okay, so let's let's actually do something here with Desmos. So let me do that on my iPad so that we can all see it. Um, oops. Okay. Dang it. There it goes. Okay. Um, all right. So this is just sort of a quick way to do something. So I'm just going to graph y equals x squared, right? Good old parabola. And let's pick a point, like let's pick this point right over here at 2 comma 4, right, which I'll roughly get with my finger. But if I zoom in on it, okay, that point there, what do you guys think the slope is? 4/1, okay? Now, when I zoomed back out, was it obvious that that's what the slope was at that point? No, okay? We had to kind of zoom in to do it. All right, so let me zoom back out and let's pick a different point. Okay, so somebody give me an x coordinate that's not 2 or -2. Way too big. 3, okay. 57. All right, so 3, well, I just screwed it up, but x equals 3 is, well, let's start over. Okay, x equals 3 would be this point up just shy of 10, right at 9. Okay, so let me sort of put that in the middle, and if I zoom in here, okay, this one's maybe a little harder to compute. What does that slope look like? Just ballpark. Okay, it would be great if the Wi-Fi would work this morning. Little harder to just kind of crunch in your head, but let me zoom in some more and maybe that'll make it a little easier. Any, now that I've zoomed in, does it look a little easier? So here's the first point, right? Do I have another point that's right on the intersection of grid lines? 6 up, 1 over, okay? Which would make the slope probably roughly 6. Okay, so 2 things we've sort of noticed here. One is we can estimate the slope of the tangent line by sort of doing this zooming thing with the graph. Okay, and we'll make that process rigorous and precise so that we don't need a graph to do it. Okay, by sort of thinking of this idea of rise over run and the 2 points on a straight line. The second thing is that we've noticed is that the slope is not the same at every point along this graph. Okay, that maybe isn't a huge shock, right? But what was the slope at one point? The first point we picked, it was 4. Okay, great, at x equals 2. And at x equals 3, it was 6. Okay, can you give me a different point where the slope is smaller than 4? Because we got bigger than 4. X equals 1. Okay, so at x equals 1, what should the slope be? Well, let's kind of zoom in and figure it out. Okay, at x equals 1, what roughly do you guys think? 2. Okay. All right, maybe you're starting to notice a pattern here, and that's because I picked a, x squared is not exactly the most squirrely function on the planet. But yeah, okay. And there's even a point where the slope is 0. Where would that be? Yeah, x equals 0 at the origin. That kind of makes sense, right? The x-axis actually is that tangent line. And to the left of 0, what's true about all these slopes? Yeah, they're all negative. And they get more and more negative the further to the left we go, right? So the slope here is negative and really steep, but the slope there is negative, but kind of gentle, right? Okay, so the slopes can be different at different places. And if we record the slopes at different places, okay, that thing is a new function. It's a function of x, and for each point x, it tells us what's the slope of the tangent line to the original guy, okay? And what do we call that thing? Or how do we notate it? What's the piece of notation? You guys remember? F prime of x. Okay, so F with a little like, well, let me just write it. Yeah, that's the word I was looking for. Okay, so F prime of x, okay, is what we're trying to come up with. Now, how have we, like, do we know what F prime of x is for our y equals x squared curve? Well, don't cheat. What do you think it is? 2x. 2x. Okay, how did you get that? So, when I say don't cheat, all right, so guess. How did you get that? And if you say you did the thing with the thing, then I'm going to smack you. Yeah, okay. But you've seen some calculus, so you know the mechanical rules for how to do this. Okay, no, it's okay. You've beaten it into it, right? So actually, when students come to us and say, "Yeah, they understand calculus because they took it in high school," what they means is that they can do that. Yeah, which is why you're here with us in this class and not, Calc 2 or whatever. Okay, so there is an algorithmic process for going from x squared to 2x, right? And we'll learn that later. Okay, for now though, what evidence do we have that it's 2x? What we have is just the following. All we have is that we've done some stuff. So when x equals 0, we got 0 for the slope. When x equals 1, the function was 1. What did the slope look like when x equals 1 when we did the zooming thing? It was 2, okay. At 2, it was, do you guys remember? 4. Okay, and it happens, of course, that 2 squared is the same as 2 times 2. Well, duh. Okay, so that was sort of coincidence. And then at 3, the function was at 9, but the slope was 6. Okay, so looking at my table of f prime values, 2x actually looks like a pretty good guess, right? But how do I know that something weird doesn't happen at 0.5? Well, I could check, yeah, right? But okay, so check 0.5. You do it. Okay, maybe it works, maybe it doesn't. Okay, say it works. How many points are there between 0 and 1? A lot. Okay, and by a lot you mean infinitely many. So, Mr. Silas, do you want to check all of those points for me? I don't think I'll be paid. Even if you are paid. Yes, I'll pay you 1/infinitieth of a cent if for each one that you check. How about that? No? Huh? Yeah, I'll pay you wise rates. Right. Okay. So, yeah, point being, we have some evidence that 2x seems like a reasonable guess, right? Because we're not morons and we can kind of look at, say, and say 0, 2, 4, 6. I wonder what's going on there. Okay. But strictly speaking, we don't know that that's going to work for every point, right? We could zoom in on some point that you pick and estimate and say, yeah, it looks pretty close to whatever 2x would be, but that's not quite enough in the business of mathematics. Okay, so what we want to do is come up with a way to sort of demonstrate that this works no matter what the point is, which we will obviously get to. Okay, now, if I drew some random kind of squirrely squiggle, right, maybe the relationship between x and f prime of x would be more complicated. If I drew a straight line, what would I get? Right, so like, let's say that I had the equation y equals 3x. What do you think its derivative would be? Yeah, 3, okay? the slope of it, right? Because, and think about this, if draw a line, just draw a line, just make it not vertical, because that one has problems. What's the slope of your line, roughly? Something, okay? All right, pick a point on your line, put a big old dot, draw me at that dot the tangent line to your curve, to your line. What did you just do? You traced exactly over the line you already had. Okay, so if the curve is a linear thing, so if we have a linear function, what is the derivative of it? A constant number, whatever the slope is of the thing that you drew. Okay, so that's a really simple function. What about if you had a horizontal line? What's the slope of that? So what's the derivative of a constant? 0. Because what's the graph of y equals a constant? It's a horizontal line. Maybe it's up here, maybe it's down there, but they're all horizontal, yes? What's the slope of that thing? Well, that's pretty easy, okay? And it turns out that where slopes are 0 is kind of important, as we'll see. Okay, so here's what we want to kind of start to think about in order to make this more, oh shit, why am I not powered? This is going to be bad because if the Mac dies in the middle of the stream, we're kind of hosed. Let me try a different outlet here. Okay, so something's wrong with the outlet on this thing. We've been having all kinds of tech issues the last few days, if you guys haven't noticed. There we go. Okay, problem averted. All right, so what's the problem with how we were approaching generating our sort of T-chart here? We were picking specific numbers, okay? Well, let's think back to algebra in high school. Okay, so for many people, what was the worst day of their life when it came to math? Well, before that. Okay, even before that. Yeah, is walking into math class the day that the alphabet got involved in math class, right? When letters suddenly became used in math class, that was when a lot of people were just like, nope, I'm out, right? And they sort of do the, you guys know the meme with the octopus that sort of nope, nope, nopes along the, yeah, okay. They're like, nope, 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 I'm out of here. Okay, so so let's get letters into it. And instead of thinking about we're going to do this at the point 2 or 3 or whatever, we're going to think about doing it at the point A. Okay. All right. So let me go to a clean sheet here. And let's say that I have a function that I want to know an approximation for f prime of A. Okay. So this would mean if I had a graph, I would go over to x equals A, I'd look at the point on the graph, I'd zoom in, I'd do this estimation of the slope business. Okay, and I'd get some number. All right, so how can we make that more precise what I'm doing? Well, let me sort of think of it this way. I'm going to think of a point A and a length or h. That's so if I go to the right of A, h units. Okay, so that's some arbitrary distance. Could be big, could be small. Okay, at here and here, what are the coordinates of those 2 points? Okay, so what are the coordinates of the point on the left if it's on my graph? Well, its x coordinate is what? Well, A, right? Because I started at A, not 0. But yeah. Okay, is that good? The x coordinate is A. All right, what's its y coordinate? Do I know? Well, okay, it maybe is 0. It looks like 0 just from my graph because I haven't drawn a scale. But symbolically, what is it in terms of the function f? It's f of, hold on, f of A, right? Because it's a specific x that I'm plugging in. Okay, do I know what f of A is? Like numerically? No. But symbolically, that's the y coordinate, whatever it is. Okay, does that make sense? Okay, let's come over to this other point. What's its x coordinate? A plus h, right? Okay, how did we get that? Well, because I labeled it, but what am I thinking here? I'm thinking I started at the point A and I went h units to the right of it. So what's my new x coordinate? A, which is where I started, plus h more units. Does that make sense? Whatever h is. Okay, so that's the x coordinate. What's the y coordinate? F of that, right? F of a plus h. Okay, now, I now have 2 points. Pray tell, what is the slope of the line that connects those 2 points? Now, you're not going to be able to tell me a number like 7 or whatever, but you can give me a formula. Okay, and Don, since you gave us the formula earlier, what do we need to compute here? So don't like.
So you need to subtract a plus h minus f of a.
Okay, so we need to do the rise over run thing, right? So what's the rise is what you just told me. Okay, so the blue slope would be, what's the rise? How do we compute that? What did you just say? Okay, right. So what did I do? I just, or he do, take the credit, right? What do we do? We just did the difference of the y coordinates, right? The rise. All right. What about the run? A plus h minus h, or a, sorry. Okay, and then we can simplify this one a little bit, right? Because what can we do in the denominator? Yeah, the a's cancel, and we just have this. Okay, so that thing, which we call difference quotient, right? It should be obvious why we call it that. There's a difference and there's a quotient. This thing is going to be the key to doing these derivatives in a precise way, okay? Because you pick a point. So like, let's go back to where we did this with x squared. Pick a value of a, like 2, for example. What was the slope that we got there? 4, okay. Pick a value of h, huh? Okay, if we do it with 3, are we going to get a really good approximation or a really bad approximation? Okay, we're going to get a really bad approximation. It'll be an approximation. So what values of h make our approximation better and better and better? Bigger or smaller? Okay, so like, would 3 work? So if he picks 3, what would you pick to make the approximation better? 300. That would actually make it way worse. Okay, so it's the other way, right? We want, well, what did we do when we were zooming in, right? This value h, when we zoom in, what's true about the value of h? Is it getting bigger or smaller? Way smaller. That's the whole point of zooming, right? Okay, so the smaller that this number h is, the better our approximation to that slope is going to be. All right, and then calculus is in the business, and we'll make this precise how we do it, of making basically h go to 0, okay, using voodoo and evil powers. Okay, so is this kind of making sense? All right, well, it's 8:52. I'm sorry I ran over a little bit. So what are we doing on Friday? Yeah, the first thing over all the pre-calculus stuff, uh, no calculator, and no, none of the questions will be multiple choice. Sorry. Okay. So there are 4 Edfinity assignments to help you guys get ready for that, and I split them into algebra, trig, logarithms, and exponentials, just basically to keep it organized. So start working on those, and if you've got questions or don't remember something, then come see me or go to the QSC or whatever. And I will see you guys Friday.